cluster. And to really do that, and to think about how structural nanomedicine is going to impact medicine in general, we have to take a step back and look at a historical analysis. If you just go 16 years ago and look at the list of top 10 drugs, pretty remarkable. Every one of them is a small molecule. And for the chemists in the audience, I say this is a time where you can reach around and pat yourself in the back and say, we did a good job. Because the pharmaceutical industry began to learn that it was very important to design molecules to be able to control where effectively every atom was within the particular drug molecule. And even the enantiomeric state became important as well. We all know that through the examples of things like thalidomide, where one enantiomer was a treatment for morning sickness and the other enantiomer was a stratagen and caused a terrible syndrome called thalidobaby syndrome. And so molecular purity, molecular structure was absolutely central to drug development. If you look today at the top 10 drugs, you see a big change. We've moved from small molecules to biologics, peptides, oligonucleotides. And if you look at the top drug, in fact, it's a nanomedicine. Oops, how did that happen? And that's the vaccine, right? So the vaccine, I think, was really important, obviously for the world, but also important for the field of nanotechnology, because it showed a couple of things. One is that complexity is important in terms of attacking drug development, being able to use more complex molecules and delivering them in effective manners. For example, lipid particles is going to be central in that particular area, and nanotech is going to play a big role there. You can attack disease in unique ways. And in fact, with respect to all biologics, that's been true. This doesn't mean that small molecules are going to disappear. That's going to be an important part of what we do as pharmaceutical developers for many years to come. But it just means that we have a whole new set of tools in our arsenal, weapons in our arsenal to ultimately attack a disease. It's proteins, even carbohydrates. They can all become the basis for new classes of drugs. And one of the things that we've learned, as I said, literally in the last 5 years, is that these require delivery vehicles. They require nanoscale delivery vehicles. So I would look at the vaccines as a first step towards structural nanomedicine, but a pretty crude step, right? It's just compartmentalization. In fact, one of the problems, of course, with those types of medicines is that we've moved from an arena where knowing where every atom was, what every atom is, every bond, and even the enantiomeric structure is important, to where if we look at the current medicines, no two particles are the same. We kind of heard about this in one of the previous talks in one of the other sessions. Somebody asked, I think it was Paul Weiss, asked a question about heterogeneity. We already deal with incredible heterogeneity. The FDA has already gotten across that path with the development of vaccines. But I think we can do a lot better. And I think we can do a lot better by using nanoscale scaffolds to go back in time and to follow the roadmap of what we learned from chemistry. That being able to structure these components in unique ways is going to give us the ability to create powerful new medicines that go beyond even our current capabilities. So it's not to say that the current advances in mRNA medicines aren't important. They clearly are important. But we can even do better if we can control the architecture of these types of materials and the placement of the medicinal components in ways that are not currently possible today. And so I want to talk about that in the context of a structure that we've been developing now for about 30 years. We refer to these as spherical nucleic acids. And these are structured forms of nucleic acids. They have really unique properties based upon that structure. And to do that, I want to start with the prototypical ones. I think many of you know that a long time ago we learned how to develop the chemistry to interface oligonucleotides with gold particles. And we developed chemistry that allowed you to load those oligonucleotides onto the gold particle, typically using the oligonucleotides capped with alkane thiols. But through salting conditions, we could load the oligonucleotides at very dense loadings so that the oligonucleotides were forced to stand upright, and then they would adopt the shape of the central particle template, hence the term spherical nucleic acid. Today we make these out of many different materials, proteins, liposomes, all sorts of inorganic and organic types of particles as well. Because what we learned was that that exercise led to a construct that had properties that were completely different from native oligonucleotides. And you know, if you think about these architectures, a spherical nucleic acid, in nature we have linear forms, we have circular forms, we have folded forms. There are no spherical nucleic acids. This is made possible through concepts from nanotechnology and chemistry. And these are powerful concepts. It's not just a descriptive term. If you look at the properties of spherical nucleic acids and compare them to their linear counterparts, they're night and day. If you look at how they bind to complementary oligonucleotides, they'll bind 100 times more tightly. You can understand that because you're pre-orienting the oligonucleotides, dialing down entropic penalties of binding. You're also creating a multivalent presentation of those oligonucleotides. That's reflected in a tighter binding constant. That's important if you're developing diagnostic tools based upon these types of particles or therapeutic constructs, because it means you can fish out a lower concentration in the case of diagnostics. In the case of therapeutics, you get higher affinity drugs, and that can lead to more potency or the need for lower doses to get the same types of effects. These types of constructs do not elicit a significant immune response. But the fourth property is one that I really want you to look at. It's illustrated in the cell culture analysis here, you can see, where we have epithelial cells, and we're treating them on the left with linear nucleic acids with a red dye. And on the right, we're treating them with spherical nucleic acids. Identical sequence, identical dye in this case. All we've done is change the structure of the nucleic acid, and you can see the result with the naked eye. Now, in a comparison standpoint, this is the exact same amount of oligonucleotide, but I want you to keep in mind from a chemistry standpoint, the particles on the right are actually 100 times more dilute than the particles on the left, because it takes about 100 oligonucleotides to make one spherical nucleic acid in this size regime. And what you see is that in the case of the linear nucleic acids, they reject. There's no significant cellular entry. You don't see the cells light up.